This video introduces the Ameba SDK build system. The content will be divided into 2 episodes. This episode covers the CMake architecture of the Ameba SDK and its basic usage guide, including how to modify existing build configurations and how to add a new set of source files. In the next episode, some advanced usages will be introduced, as well as common issues and solutions. First, the CMake architecture of the Ameba SDK will be introduced. It is divided into 4 levels: SOC, MCU, firmware, and component. Under the project directory of each SOC, the CMake list file is the build entry point. Each SOC may contain multiple MCUs. For example, the application processor and the network processor are 2 different MCUs. Different MCUs use different global build configurations, while all firmwares within the same MCU share the same compilation toolchain and global build configurations. Each MCU may contain multiple firmwares with distinct functionalities. Among them, Image 1 provides the bootloader functionality. Image 2 provides the application functionality, where user applications are generally built, and Image 3 is optional, providing trust zone-related functionality. In each firmware, multiple components can be added as needed. Components are located in the component directory of SDK. Different components take charge of different functions. For example, AT commands and OS both belong to components. The CMake list file in their respective directories defines the corresponding build rules and private configurations, and private configurations can override global ones. Firmwares are independent of each other. Users can modify build options, as well as add or remove components in the firmware CMake lists file. Take the RTL8721DX chip as an example. Navigate to the aimbad+/project directory in the component/SOC directory. The CMake lists file in this directory is the build entry point. There are 2 MCUs in this chip, KM0 and KM4, where KM0 is the network processor, and KM4 is the application processor. And the MCU CMake lists, such as KM4, several required firmwares are added. In the firmware CMake lists, multiple required components are added. The CMake directory in the SDK provides the underlying CMake scripts. Inside it, the flags directory contains global build configurations, including compile and link options. Based on their scope, the flags are divided into a common part and several MCU-specific parts. The common flags will take effect for all MCUs. Navigate to the CMake/flags/common directory. For example, in the common compile options, the -w error flag will turn all warnings into compilation errors. If compilation warnings are allowed, you can either remove this flag here or override it later by modifying the compile options in your own components. Compile and link options under CMake/flags will take global effect for the corresponding MCUs, unless overridden by subsequent configurations. The MCU-specific flags mainly consist of architecture-specific configurations, which you can reference for different MCUs. In addition, the API wrappers for basic functions and variable definitions are provided in the CMake directory. The toolchain directory contains scripts about the compilation toolchain, which will be checked by the build system before starting the build process. There is also an example directory under CMake, which contains basic CMake usage examples. The following explanations will be based on these examples. Meanwhile, the CMake directory includes a CMake template file. Before modifying compile options, build configurations, or adding new CMake list files, users are recommended to read this template file first and follow its usage when making modifications. Below is an explanation of common usage with specific examples. You can create an external project outside the SDK directory using the ameba.py new project command, which allows independent maintenance of the external project directory and facilitates secondary development. We have created an external project, named My Project here. The CMakeLists.txt file in this project serves as the build entry point, and the app example function defined in the app main.c file. Under the app example directory is the application program entry point. To build this external project, first run the env.bat script to configure the Ameba environment. Then execute the build command ameba.py build and the external project directory. Once the build starts, a dedicated build directory will be generated automatically. Its name begins with build, followed by the selected SOC model. Inside this directory, the build folder stores build intermediates, and the menu config folder stores configuration results. A build done message will be displayed when the compilation succeeds. After compilation, you can check the intermediates for each MCU in the build directory. Each firmware will ultimately generate an AXF file. These AXF files are processed and packaged to generate the final bin firmware files, which you can flash onto the chip. You may need to modify or extend your application, add files or components to the project, and adjust the build configurations. We provide several usage examples, including adding a set of source files, adding an independent third-party project, which may be implemented with CMake lists or Makefile, adding pre-built library files, and linking them to the current firmware. This section will explain how to modify existing build configurations. Users can refer to the template file in the CMake directory for the available build configurations. Take an existing component as an example. Its build configuration is divided into a public part and a private part, differentiated by their scope. The public part takes global effect for the current MCU and is not restricted to the current component. The private part applies only to the current component, used for compiling and generating the current library, and is inaccessible to parts outside the component. The public part includes header directories, macro definitions, and library files. All build configurations are modified through list append operations. For example, in the CMake lists file of this component, the current directory is appended to the global include directories in the public part, meaning header files under this directory are globally visible to the entire MCU. The private part includes source files, header directories, private definitions, and compilation options, which are only valid for the current component. In this example, source files are added to the private sources section. Finally, an internal library is compiled and generated using a dedicated API. These private build configurations take effect through this API, while public build configurations take effect via Ameba global prefixed APIs and are appended to the global build configurations. As we can see, the include directory is added to the public part, and it is not added to the private part again. Build configurations added to the public part do not need to be duplicated in the private part, as they apply to both the current component and all components within the MCU. To modify the build configuration of this component, simply use the list append operation to append content at the end. For instance, to add a new foo.c file, you can append it directly or in a separate step. The two methods are equivalent. Other build configurations can be modified in the same way. Several distinct APIs are provided for list append operations, each suitable for different scenarios, and they can be used in combination with kconfig. In summary, to modify the build configuration of an existing component, users shall first refer to the CMake lists template file and modify the public part and private part of the build configuration as needed. The modification is implemented through list append-based APIs. Content can be appended directly or appended based on specific configuration requirements. The second common usage scenario is to add a new set of source files to the current project to extend the application functions, which requires modifications to the corresponding build configurations. First, copy the corresponding example to the current external project directory. The example directory contains several source files and header files. A foo function is defined in the source file, which needs to be referenced by app example. First, write the CMake build rules for these source files by copying the CMake lists template file and modifying it accordingly. In the public part of the modified CMake lists file, the public include directory is appended to the public includes section, meaning these header files can be referenced by other components. In the private part, the source files are added, and the private include directory is added in the private includes section. The header files in this directory cannot be referenced by other components. In addition, private macro definitions and private compilation options are added. The options here will override the corresponding global compilation options, meaning warnings within the current component will no longer be treated as errors. Finally, the add internal library interface is used to create a target named foo, which will outputs the libfoo.a library file. After modifying the CMake list file, the foo directory must be added to its parent directory before calling the functions defined in it. For example, call the funcfo function in the app example /app main.c file. Execute the build command and wait for the compilation to complete. In this example, two subfunctions, func_a and func_b are defined, where func_b is controlled by a macro. Func_b is called only when the macro is defined, as shown in the subfunction.c file. Func_b is compiled only when the macro is defined. Combined with the CMake list file, the macro definition is added to private definitions to control whether func_b is compiled and called. If the macro definition is not added, func_b will neither be compiled nor called. After build done, we can check whether funcfoo is compiled successfully. Navigate to the build directory and check the map file of km4's image 2. It can be seen that funcfoo has been correctly compiled into libfoo.a and called by the source file app example /app main.c, which indicates that the modifications to the CMake list file are correct and the function is effective. If the corresponding firmwares are flashed onto the chip, the corresponding log will be printed. Here is a summary of the above operations. To add a new set of source files to the build system, first create a new CMake list file for these source files and modify the build configurations based on the template file. Use the aforementioned list, append operations for modifications, and select different APIs according to your needs. After setting the build configurations properly, use the Add Internal Library API in the private part to make the configurations take effect. This API is used to compile the source files into a static library target and link it to the current image. Finally, use APIs prefixed with Ameba add subdirectory to add the directory containing the newly added source files as a subdirectory. Multiple forms of add subdirectory APIs are available for selection. The if or if not logic among them can be used in conjunction with menu config, while the if exists condition checks whether the directory exists, which is suitable for scenarios where the directory may not be present. This concludes the content for this episode. Thank you for watching.